Hey, I'm Mark. I'm a first year PhD student, and my PhD is in nanotechnology, so I'm a nanotechnological technician, I think is what we like to be called. I look a little haggard because I'm a mature student. I was working in pharmaceuticals for 10 years, so I'm not like a chemist. But jacked that in, and now I'm developing solar cells, or next generation solar cells materials. So I'm here in Lund in Sweden at MAX-lab, which is a synchrotron. So why am I at a synchrotron? And what is a synchrotron? So what a synchrotron is imagine a big, let's go with a bike tyre. It's pretty grand. Maybe I should have said an inner tube. I'm in a tube. Yeah. Like, so you've probably seen CERN actually, the Large Hadron Collider. It's amazing, but people just don't understand how soft Brian Cox's hair actually is. It's like a unicorn's tail. But let's stick with our bike tyre. So, electrons, I'm whizzing my finger. Not horrible. What we do is we whiz electrons around this bike tyre really quick, like really faster than that, like near the speed of light, and then we bend them in magnetic fields, and when we bend them they kick out a bit of light. So imagine you're driving and you're being attacked in a car, and then you see a roundabout, and what you can do is you can sort of like reach over, open the door, spin around the roundabout and kick your attacker out the door, so the G-force takes him out. If you're ever in Sweden, you have to try these. They come in different packets. They're always black, licoricey things, but they're covered in ammonium chloride. Like, absolutely minimum. Better than the coffee, but you gotta try it. It's weird. It's like salty, but then it tastes of ammonia, and then it's licorice. I don't like them. And the electrons fly around at the speed of light, bend them, and they kick out light. And that light is an X-ray. So why do we look at an X-ray? Well, an X-ray's got the same wavelength as atoms. Earlier I said that the wavelength of X-rays is the same as atoms. It just doesn't even make any sense. What I meant is the wavelength is the same as the bond length between atoms. So that means we can study atoms with X-rays. Why can you study them with X-rays? Why does it matter the same distance? It's because they interact. So if you imagine you're Godzilla and you're being attacked now, imagine you're Godzilla and you run through a forest, and you can run through it all day because you're so massive. You just run through the trees, and trees get trampled. You don't even notice. You might get a splinter, but you're not that bothered. So you're too big to interact with the forest. Imagine you're an ant, and you could live on this tree your entire life and never really know you lived on a tree. So you'd run around it, it wouldn't bother you. You might go on a leaf one day and that might blow off, but it doesn't matter. But say if you are a badger and you are chasing a squirrel. So then the forest really matters, because you've got to interact with the woods, you've got to run around it, the squirrel might go up a tree, you can't go up a tree because can badgers go up trees? I don't know. But the important thing is, you're going to run around this forest and you interact, and that's the same with X-rays. We use an X-ray source to look at atoms. I could go into a bit more detail later, or I might do. But the reason I'm making this video is because it's 1 in the morning, I'm a little bored, going a little bit nuts. I've been on nights because I'm the new boy, and I sort of messed up. So I'm going to try and fix it, and you're going to help me. Okay, so here we are, and here's the synchrotron. So you can't see much of it, and what's amazing, this place is all built of wood. So try to look at this at the same time. So that's just some shelves. terrible start. Behind this wall, and we're following all them pipes, the synchrotron, the bike tyre, that's behind there. And if we look, so you can see, is my finger, is it going to work? Yeah, it's going to work. Where I said you kick an assailant out of a roundabout, so you kick the light out, this is where the beam line comes out. So we've got X-rays firing down this line to that bad boy, which looks mint. This is an XPS, this is an X-ray photon emission spectroscopy. So this bad boy is not as complicated as it looks. You know, I'm spinning the camera around just to make it look more complicated and make me look smarter. So we've already talked about the X-rays coming in. So X-rays come up that line and they get fired. Well, I've got a light here. What can we see? What can we see? See that? I need to get my finger in. See that cone? That's the analyzer. X-rays come in just below it. I'm going to put the sample down, but the bottom line is the X-rays fly in, bounce off the sample and go through an analyzer. Electrons, the X-rays knock out electrons which go in the atoms. So we fire the X-rays and we blast them into our target. What happens there is you've got loads of electrons which make up atoms. So you know that atoms are made of protons, neutrons, electrons. So you blast out an electron from an atom, and the energy of that electron is specific to that atom. So you just know what atoms you've got. Is the basics of it, and you know what that atom's bonded to. So you can, and because this is quite a low, pretty close to you. These electrons are quite low energy, so what it means is you can only analyse the top layer, so you literally analyse the top 10 nanometers or most. All this stuff's just all fancy stuff to make us look clever. Not true, a little bit. So we've got this big thing, but all that does is move a sample up and down. We've got pumps to get the air out, because we have to do all these experiments under ultra high vacuum. Gas lines, just to stick stuff in there so we can stick different gases. I'm putting an organic molecule in at the moment. Pumps again, just pumps to get rid of the air. So we've got two chambers, we've got top chamber and the bottom chamber. So this is the top chamber, so this is where we add all our gases in, and the bottom chamber is where we do our analysis. All the rest is just pumps. Yeah. Pumps everywhere. Coffee's proper ming in there. Right. See? This is hard to get in. Hang on, I need to get my finger in it. Where's my finger? There's my finger. Now you see that little black square there? That is my sample. So that's titanium dioxide. So just think all this and that and that and that. Pumps everywhere. It's just to analyse that little bit of titanium dioxide, which is 0.63% of the Earth's crust. And you use it for sunscreen, and you use it for all these different things. It's a wonder material, which is why I'm working on it. So that's the black thing, is a titanium dioxide, and that's one of my samples. My other sample's on the back. And unfortunately, I didn't do a wire up properly, so the wire is hanging in front of my sample and getting in the way when I shine an X-ray on it. So I've got to try and get rid of it. So I've been using this thing. Oh shit! Hang on. That's not good. There are actually scooters somewhere, so you can go around the whole place in scooters. Sounds cool, but I'm a bit nervous about going to get one because there's got some bigger boys on them. No, it's alright, it's alright. Right, I'm just gonna... Ooh. That doesn't sound good either. Ah. Press the button, thing moves round. So I want to see the samples behind there. There you go. Let's have a look, let's have a look. And you can see that red and yellow wire, that's a thermocouple. That just tells you the temperature. You got them in your boiler. That's the thing which always goes wrong, and some arsehole charges you 300 quid to change. Right, so there's my other sample. See this little transparent thing on the copper? Nanoparticles on there. You must have at Daily Mail always says it's going to kill everyone. So that is what's going to kill you. You can see that bit of wire is just in the bastard way. So we need to get that wire out of the way. I'm trying. I can wiggle this. So I'm trying to sort of just move it around and wiggle it into place. It's not really working too well. So I'm going to have another wiggle, and then we're going to learn some more science. I've been wiggling it. So yeah, I think I fixed it, because if you see that red wire, I've wiggled this little plate thing and jammed it behind the copper. Proper like, I'm from a seaside town, so I used to play with them things where you can win a cuddly toy with the cranes. So, you know, I'm pretty good at this science stuff. So yeah, that's there. So that means I can actually have a look at this nano crystal thing now. On to the next, onwards and upwards. Yeah, that was one of the bigger boys I was telling you about earlier. No, I'm not going to get on that scooter, am I? Not going to happen. So I'm going to lower it down from the sample prep chamber into the analysis chamber. Down. Yeah, there's a little speed button, but you know, it's not complicated. Down. So I'll just come into another little snag. So this is my sample manipulator. Oh, I can hear that. So it's getting a little bit squeaky. So I just thought I'd lube it up. So just gonna look for some lube. A little bit of lube on. Let's see what that does. Hang on, still squeaky. Come on, shh. And there you go, that's science in action. Science in action. Here it comes. And there's a table tennis table there too, you know. Well, not many people know this, well everyone I know, but I was a Great Yarmouth under 15, under 17 town champion. They can't take that away from me. It's on its way. They can kick me off my course for not knowing enough about science, but they can't take that away from me. So now what I've got to do is I've got to line that little crystal you can see on there with the nanoparticles, ones which kills everyone. Doesn't really kill anyone. If you take one thing away from this video, it's that nanoparticles don't kill everyone. So I've lined it up by eye. Got 5 some X-rays at it. Yep, it's nearly 4. Stop. That's not really working properly now, but I've an idea. Yeah. All right. I feel like this. I'm going to monitor the signal, we'll look for titanium, and move the sample around. So if I move the sample and the signal goes down, it means I'm missing. If I move it goes up, it means I'm hitting it. Sample in the Y direction, the X direction, the Z direction, and we've already seen the change in the angle until that number gets as big as it can possibly be. I'm just going to show you a classic hazard of being a scientist. So you got your spectrum up. You go what will zoom in? Use the mouse. Nothing happens. and then you realise you got the wrong mouse. Egg on your face, and there's nothing you can do about it. Look at that, that is an absolute stonker. Awesome, so that means we've got a lot of counts, which means we can analyse our crystal and we're ready to rock. So let battle commence. Right, boys and girls, it's summary time. So now we're going to go through and we're going to put together everything you've learned today. And there's been a lot. Start off, synchrotron. So synchrotron, bike wheel, accelerating electrons, speed of light, when they bend, kicks out light. We're interested in the X-rays it kicks out. Why we're interested in X-rays? Because the wavelength of the X-rays is similar to that of the bond between atoms. That means we can look at the atoms. Right, a synchrotron. So what we're looking at, we're looking at titanium dioxide. Why are we looking at that? It's potential solar cell material for the future. There's loads of it, it's safe, it's doesn't corrode. The only problem is it doesn't absorb the right amount of light, so it's not very efficient. So what I'm doing is I'm looking at different kinds of titanium dioxide, different crystals, nanoparticles to a large surface area, bonding things onto the surface to alter how much light it absorbs, because we want more efficient cells. What I'm specifically looking at is to bond, to use titanium dioxide to split water. So take water, stick some titanium dioxide in a pond. So why do we want to split water? Well, the fact is, like, it's not always sunny at night. In fact, it's never. Well, low battery. These are for staff to say thank you. Really heavy. Okay, when it's dark, you're not getting solar power, so what we need to do is we need to store the solar power, which we say use in the day and don't need. So that by that we can split water. So hydrogen, so we've got hydrogen fuel. We burn that. You burn hydrogen fuel, you make water. You burn like natural gas, you make carbon dioxide, and polar bears die. You don't want polar bears to die. They could be right bastards. But we want to save polar bears, so we want to get rid of the greenhouse effect. We want to, save stuff and stop drilling in places and just be nicer, really. Look how bloodshot my eye is. It's disgusting. Right then, so you've probably seen me get more tired and my eyes shut a bit more on every single shot. It's 6 o'clock in the morning. It's light outside. Beautiful sunny day here in Sweden. I hope you've enjoyed this educational video. I hope you learned a lot. I hope you're going to go green, save the world, man. It's like a unicorn's tail. I'd just like to say a couple of thanks. I'd like to say thanks to Tom and Wendy for teaching me everything I know, everything you've heard in this video, all my knowledge on physics. I'd like to thank the guys at MAX-lab for just letting me run around without any adults to watch over me, so that's been a lot of fun. I've learnt a hell of a lot, so thanks very much you guys too, and thanks for watching.